Good morning.
Good morning, ma'am.
Good morning, ma'am.
Good morning,
Good
ma'am.
morning. So today I'll start with expenditure minimization. As I mentioned last day I told you to practice some problems based on utility maximization subject to budget constraint. Look at the theory and practice some problems from Henderson and Quant. So could you start practicing those things? The standard problems, at least?
Ma'am,
Yes,
I
ma'am.
had mailed you the PDF of the version of the book I have. I couldn't find any questions or exercises from that. Like the theory portion was there, but I couldn't find questions.
Same problem, ma'am.
Who are you?
Ma'am Kritika.
Kritika. Kritika, in Henderson Quant book, you don't have any exercises. No, I didn't get
I
your
could
version somehow. Or I don't know where you posted in the Google Classroom.
no ma'am, I had mailed you.
No, I didn't get your mail with Henderson and Quant. Uh, for rest of the students, the version I sent you, there is no exercises. Anyone else? Okay. Okay, so in that case, I have to check and I have to, it's a bit difficult. However, I need to scan the things. Okay. So tomorrow onwards, I'll go back and I'll be able to send you the problems, or during the class I have to mention that. You know. So at least theory part, I hope you could cover in the weekend.
Yes, ma'am.
Yes, ma'am.
Okay. Okay. So let's start with the expenditure minimization. Some students have sent some questions regarding constant optimization too. So I'll clarify everything. However, let me first start with the expenditure minimization and then I'll come to the queries. So last day, we mentioned about a context where I have a single indifference curve corresponding to the utility function I have a possible number of budget lines. Among these budget lines, I am picking and choosing one which is making a point of tangency between the indifference curve and the budget line. So if we look at the diagram, so this kind of thing we did in the last class, this kind of thing. So I have, one objective function, that is the utility function, okay? And subject to, budget constraint, I am trying to find out, sorry, look at this one, subject to this income constant, the second diagram, sorry. Subject to income constraint, I'm trying to find out one giving me the maximum level of satisfaction. So I have a bunch of indifference curves, indifference map, and I have these income constraint given by AB. Okay, subject to that, I am picking and choosing an indifference curve when the budget line and the indifference curve making a point of tangency. And actually, I am solving for this particular point. And deriving the values of x1 star, x2 star. If I measure x1 along the horizontal axis, x2 along the vertical axis, following these particular context, I am trying to find out x1 star, x2 star. Today, I'll discuss this kind of problem. So I'll have a specific level of utility. Okay, so utility is the constraint. I'll adjust the income or the budget or the expenditure so that I can attain this particular level of utility. I'll adjust my budget or expenditure so that I can attain this particular level of utility. So today I'll discuss this kind of problem. Now this one, which I discussed in the last class, in terms and terminology of linear programming, is called the primal problem. Maximization of utility subject to income constraint is called the primal problem. And this one is called the dual problem. Do you have any knowledge of linear programming? LPP? Linear?
Yes, ma'am.
Just basic knowledge from like
What have we
plus
did in 12?
Yes, just basic only we need. So, for every primal problem, there will be a dual problem. I hope if you have preliminary knowledge, at least you did this too. For every primal, there will be a corresponding dual. So,
No,
at
ma'am.
least you have
No,
an
ma'am,
idea.
we didn't do.
No, ma'am. No, ma'am. We did not know this.
Are you familiar with the primal and the dual problem? What is meant by a primal problem? What is
No,
meant by
ma'am.
a dual problem? So, what knowledge you have? You told that you have some introductory knowledge.
And we just did graphs like maximization,
It's
minimization.
only graph drawing and subject to constant.
Okay,
Yes,
so
ma'am. We just do the graphs.
okay, and in the graph, do you have any idea with respect to graph, which one is the primal and which one is the dual?
No, ma'am.
We have,
Okay, so
Actually, these terms are new.
yes, these terms were not there.
okay, so you should Google for these two terms. Please note down. In linear programming, what is meant by a primal problem and what is meant by a dual problem. Okay, what is meant by a primal problem and what is meant by a dual problem. Please check these two definitions, primal and dual problem. And note down that for every primal problem in linear programming, there will be a corresponding dual problem. Okay, now in utility maximization context, or in the subject of utility maximization, we consider maximization of utility subject to income constraint is a primal problem. Okay, whereas minimization of expenditure subject to a fixed level of utility, subject to a fixed level of utility, is called a dual problem, is called a dual problem. Okay, then add one more sentence. If the constraint is non-linear, if the constraint is non-linear, the problem is called a non-linear programming. If the constraint is non-linear, in that case, it is called NLP, non-linear programming. NLP, non-linear programming. Just put these points and please check, what is meant by a primal problem, what is meant by a dual problem, or you can follow any mathematics book if you have with it, if you have the book with you, any book of linear programming, just check these definitions, nothing else. So I hope you are understanding. Last day we discussed this kind of problem where we have a budget constraint and where we have a set of indifference curves or the entire indifference map, and subject to these budget constraint, we maximize the utility. We try to attain the highest level of indifference curve. Okay, so are you understanding this issue? Last day we did this thing. Can you relate this?
Yes,
The
ma'am.
last day's exercise? Okay.
Yes, ma'am.
Today we will just do the reverse. Today we will just do the reverse, you know. So there is a particular level of utility, and somehow with the help of some compensation or with the help of my own income, I'll try to attain this particular level of utility. Okay. Ultimately, the solution will be the same, you know, when the indifference curve and the budget line are touching each other, we will get the solution. So the first order condition will remain same. Actually, in the if you consider the first order condition, it is nothing but the point of tangency between the indifference curve and the budget line. So, you know, ratio of marginal utilities will be equal to Px by Py, or MRSXY will be equal to Px by Py for both the context, for both the primal as well as the dual problems. However, the second order condition will vary a bit because the first problem is the maximization problem and the second problem is a minimization problem. Okay, so the border Hessian determinant and or the nature of the border Hessian determinant will vary between the two contexts. Okay, so this is the, and conceptually as we proceed, you will find that today's demand will be called the compensated demand, or this demand we will call the Hickshian demand for the commodities, whereas the demand we derived last day, those demands are ordinary demand or the Marshallian demand. Those demands will be referred to as ordinary demands, whereas today the way we will actually try to find out the equilibrium, this is based on compensation principle, and therefore we will call these demands the compensated demands. So let's look at the problem.
Ma'am, can you please repeat what you just said? My connection got cut a bit.
I said that last day the demand we derived we call the ordinary or the Marshallian demand, and as we proceed for today's class you will find that today the way we are deriving the demand, you know, with the help of some compensation, we are trying to reach at the fixed level of utility. This kind of demand will be called the compensated demand or Hicks compensated demand. So today the demand we will derive will be called the Hicks compensated demand, whereas the demand we derived last day is called the Marshallian demand. So please look at the slide. This is a dual problem of utility maximization. Suppose a government taxes or subsidizes the consumer in such a way as to leave his or her utility unchanged after a price change. Okay, so you have this idea, you know. So there was one original solution. Now there is a change in the relative prices. However, there will be some kind of compensation principle, negative or positive compensation principle. Now, if the relative price of the commodity falls, in that case, we will tax you. If the relative price of the commodity increases, in that case, we will subsidize you. So in the previous case, we will take away some money from you. In the other case, we will add some money in your basket, you know, or in your pocket. So all these things will happen. So suppose a government taxes or subsidizes a consumer in such a way as to leave his or her utility unchanged after a price fixed. In other words, we have a fixed level of utility, or we have a specific indifference curve, Even after the change in relative price, the consumer will like to remain on that indifference curve. So this is the idea. Suppose this is done by providing a lump sum payment that will give the consumer the minimum income necessary to achieve his or her initial utility level. So, implicitly, I'm considering an increase in price. This is the common thing. Theoretically, it is possible to consider the reduction in relative price of the commodity. However, in our everyday life, the more familiar context is the relative price of the commodity is increasing. So suppose the relative price of the commodity is increasing and the government is providing a lump sum payment that will give the consumer the minimum income necessary to achieve his or her initial utility level. The consumer's compensated demand functions give the quantities of the commodities that he or she will buy as functions of commodity prices and a fixed level of utility under these conditions. So last day, the demand we derived were functions of P1, P2, and M, income. And today, the demand we will derive, that will be function of P1, P2, and U star or U naught, a fixed level of utility. So a fixed level of utility will be there, or fixed level of utility will appear as one of the parameters in the equation. These compensated demands are derived by minimizing the consumer's expenditure or budget subject to the constraint that his or her utility is fixed at a particular level, say U bar. Any question regarding this background? Is it okay? So if the thing is okay, in the mathematical part, we will write one objective function and we will write the constraint. So here, the objective function is the income, the budget. That is, M is equal to P1 x1 plus P2 x2. So this is the budget. This is the income. And we will like to minimize it. So minimize P1x1 plus P2x2. Minimize P1x1 plus P2x2. And this is subject to the constraint U naught is equal to U of x1, x2. U naught is the specific level of utility. It is given by a specific indifference curve. It is given by a specific indifference curve. The required Lagrangian expression for optimization is given by L is equal to what we do, we add the original objective function with the constraint using a Lagrange multiplier. So we are exactly doing that. L is equal to P1x1 plus P2x2 plus lambda within bracket U naught minus U of x1, x2. U naught minus U of x1, x2. Okay, since I'm writing a constant minus the variable part, I'm using the plus sign with the Lagrange multiplier. However, if I write the constraint as U of x1, x2 minus U naught in this format, in that case, I'll write minus lambda. So in that case, the expression will be L is equal to P1x1 plus P2x2 minus lambda U of x1, x2 minus U naught. So please remember this thing. Any question regarding the Lagrangian expression? So as we understand how from the objective function and the constraint we are
Ma'am, your voice is breaking very badly.
the Lagrangian. Okay. In this,
And we can't hear
Ma'am,
you.
your
there is
voice is
some internet
breaking.
Ma'am, your
problem.
voice is breaking.
Is it okay? Is it visible now?
Yes, ma'am.
Am I audible?
Yes, ma'am. Yes, ma'am.
Okay. So what I am telling that once you get this expression, in the next step, you have to take several first order conditions. You need to consider the first order conditions. So please do all these things in detail. So what I am doing, I am considering del L by del x1 that is equal to 0, del L by del x2 that is equal to 0, and del L by del lambda that is equal to 0. Now, from the first expression, del L by del x1, we are getting P1 minus lambda del U by del x1 is equal to 0. Okay. From where we are getting all these things? Here the expression is P1 x1. So if I take the derivative with respect to x1, it will be P1. Here plus lambda, here the minus sign is there. So P1 minus lambda. And from this expression, del U by del x1, del U by del x1. So the first order condition will be P1 minus lambda del U by del x1 is equal to 0. So from there, we are getting the expression P1 is equal to lambda by del U del x1. Similarly, del L by del x2, del L by del x2 is giving P2 minus lambda del U by del x2 is equal to 0. So from there, we are getting equation number 2, P2 is equal to lambda del U by del x2. Finally, the third equation will be del L by del lambda, which will give us back the entire constant. Always this will happen. If Lagrange multiplier, we will get back the constraint. We will get back the constraint. So here also we are getting back the constraint u0 minus u of x1, x2 is equal to 0. Now, as we know from the earth, if I combine equation 1 and 2, we are getting P1 by P2 is equal to del U del x1 by del U del x2. In other words, we are getting P1 by P2 is equal to MRS x1, x2. So as I mentioned, the first order condition will remain intact between the primal and the dual problems. Between the primal and the dual problems, the first order conditions will remain intact. We will get the same first order condition, same equation. Okay. So that we are getting, and that we are solving with the specific level of utility. So we will solve that particular equation, that is P1 by P2 is equal to MRS x1 x2 with this expression, and we will get the optimum solution in terms of three parameters P1, P2 and U0. So this will give us x1 star and x2 star, And these are the functions of P1, P2, and U naught. So these are Higgs compensated demand curves as utility remains fixed at a specific level U naught. Any question regarding the first order condition, regarding the solution? Any question? Are you
Ma'am,
understanding? Yes. Yes, what is the question? What's the question?
ma'am, in the expression u naught minus u of x1 comma x2, ma'am, that part, what does that expression taken separately mean?
What does that expression?
Like taken just that expression mean u naught minus u of x1 comma x2. Does it have any intuitive meaning?
This one, P1 is equal to lambda del U by del X1, or P1 by P2 is
No,
equal
ma'am.
to MRS
In the
X1.
Lagrangian. No, ma'am. In the Lagrangian, u naught minus u x1 comma x2. I was asking whether it has any intuitive meaning.
Why this should have intuitive meaning? This is the constraint. This is the specific level of indifference curve. This is indicating the utility remains fixed at a particular level, and subject to that, we will try to minimize the expenditure. So subject to this condition, we will try to find out the expenditure minimizing solution. Okay, the intuitive meaning, there is no question of separately understanding the intuitive meaning. This is the focus of this entire thing. This is the focus. We are trying to minimize the expenditure subject to a specific level of utility, or given a particular indifference curve, we are trying to find out the expenditure which will help us to attain that fixed level of utility. Okay, so this is the focus. No intuition is required here. Okay, any question?
Yes, ma'am.
Are you getting my point? Anyone else? Any question regarding the first order condition? Regarding the solution? Any question? So we will move for the second order condition then. We have del L by del X1, del L by del X2, del L by del lambda. So we have to consider del square X1 by, del square L by del X1 square, then del square L by del X1 del X2, then del square L by del X1 del lambda. So three derivatives we can find out from the first order condition, that is from del L by del X1. Then we will derive del square L by del X2 square, del square L by del lambda square, and we will apply Young's rule under certain context, and we will get these 3 by 3 bordered Hessian determinant, L lambda lambda, L lambda 1, L lambda 2, L1 lambda, L2 lambda. This is the border. So it is del square L by del lambda square. This is del square L by del lambda del x1, del square L by del lambda del x2. This is del square L by del x1 del lambda. Actually, this and this will be identical by Young's rule. And this L2 lambda, that is nothing but del square L by del lambda del x2. And this will be again similar to L lambda 2. Then del square x by, del square L by del x1 square, that is L11. L22 is del square L by del x2 square, and del L12 and L21, this is del square L by del x1 del x2. Okay, so these are the expressions you need to derive from the first order conditions, and you have to put the values here, and you need to check whether it is less than 0 or not, because For the minimization, you need the bordered Hessian determinant should be negative. Okay. For maximization, you need alteration in sign, etc. However, for minimization, you need all the bordered Hessian determinant instead of 2 commodities. If it is a 3 commodity world and you define the bordered Hessian, for the minimization, you need that bordered Hessian determinant will be also less than 0. So if this bordered Hessian determinant is less than 0, then the x1 star and x2 star you derived, these are giving the expenditure minimizing solutions. These are giving the expenditure minimizing solutions. Any question, anything I need to clarify once again? Anyone? Understanding the matter? Yes or no?
Yes, ma'am.
So once you understand these issues, next, I hope you are understanding, I will move towards indirect utility function, indirect expenditure function, etc. As we did in case of unconstrained optimization. In case of unconstrained optimization, using the indirect value function, we derived the input demand. Here, we are talking about the commodities rather than inputs. So this is another way, starting from the value function and derive the commodity demand. So starting from the optimum value function or starting from the maximum, we can derive x1 star, x2 star. Similarly, in context of compensated demand, starting from the value function, expenditure minimization amount, we can again derive x1 star, x2 star. So in the next step, I'll go for that. However, before going to indirect value function or indirect utility function, indirect expenditure function, and deriving the commodity demands using these indirect functions, I'll try to give answer to your questions, some questions sent by you. Okay. In utility maximization by Lagrange method, we have nowhere restricted that the solution that we obtain will be non-negative or in fact positive quantities. Okay, so you are thinking that here no way I mentioned, here the mechanism we are using is the strict convexity of the indifference curve. Strict convexity of the indifference curve, and we are considering straight line budget line, So when we consider a strict convex indifference curve and budget line in this way, generally we will get the solution in the commodity space. Generally we will get the solution, always we will get the solution in the commodity space. So this is the answer to this question. Additionally, we can mention that this is a linear programming problem. In a linear programming problem, the default restriction is the variable values should be non-negative. Okay, so since it is a linear programming problem, it is either primal or dual problems, the solution should be non-negative. All the solutions will be non-negative. So this is the implicit assumption. This is the implicit assumption here. So in this way, we are accommodating the fact that the solutions will be, non-negative solutions. The solutions will be non-negative solutions.
Will you repeat the first point once again?
Yes. Here, the way we are doing or placing the problem, we are considering strict convexity or quasi-concavity of the objective function. We are presenting quasi-concavity of the objective function, or we are considering an objective function which is quasi-concave in nature. Okay. Now, along with that, we have a budget line. So if we consider a quasi-concave objective function and we consider a linear budget line that is indicating a solution which should appear in the commodity space, Commodity space means X1, X2 space. Okay, this is number one. Number two, it is a linear programming problem. In a linear programming problem, always we consider the restriction that the values of the variables we are deriving, those should be non-negative. Okay. So together the two conditions, that is strict convexity will not allow you to have corner solution. So strict convexity as well as the implicit assumption of the linear programming, ensuring that we will have a solution for the commodities which will be in the positive quadrant. This is the thing. The second query was, I didn't mention anything about the boundary solution. Now again, the answer is here we are working with a quasi-concave function, a strict convex indifference curve. And therefore, we are not considering the issue of corner solution. Actually, using the Lagrangian multiplier, we are getting MRS XY is equal to PX by PY. The way we are doing this, we are developing the first order condition, solving the first two first order conditions, or with the help of first two first order conditions, we are getting the equation MRS XY is equal to PX by PY. Now for the corner solution, we need either MRS will be greater than PX by PY along the entire commodity space, or MRS XY will be less than PX by PY in the entire commodity space. So these are all special cases, and the conditions will be something different compared to the first order conditions we are getting from the Lagrangian expression. So when we are going for this constraint optimization exercise, we are getting a solution in the commodity space, non-negative solution in the commodity space. It has been designed in that way. However, if you are interested about the corner solution from your earlier knowledge, you know that here MRS XY will be never equal to PX by PY. Rather, one will be greater than the other, isn't it? So, already you learned, or the first order condition, or the requirement for getting a boundary solution. In case of boundary solution, you are facing the problem of corner kind of thing, which is not totally differentiable. So here we are handling the utility function or the indifference curve, whatever you mention, that is differentiable. In context of corner solution or the boundary solution, there will be no issue of differentiability, because there will be a kink kind of thing, or the axis will become the part of the indifference curve. So all these issues are coming. So in the very beginning, I mentioned about twice differentiable continuous function or continuous curve we are considering. So all these issues are not appearing. Having boundary solution, etc., that is not appearing. For the boundary solution, we already learned the condition. We already know the condition. I don't know whose question was it. Whose question was it, because you sent it from the general mail. Whose question? Okay. The person is not there. Okay, I don't know, whose question was there. So, and so I don't know whether the person is satisfied or not. Okay. So these are the answers to these questions. And there was another thing, what will happen if we consider the non-linear constraint, that is another module, in fact. So that is there in the syllabus. So here we are typically handling the equality constant. We are not handling the constraint which is not linear. So after completing this thing, we will discuss about the non-linear constraint, or maybe ZH will discuss about the non-linear programming part. Okay, so that is the answer to this question. What will happen to the non-linear constraint? So in this periphery regarding the boundary solution, or regarding, why there is no added constraint to ensure that we will get a solution in the commodity space, I think this is clear. If anyone have any question in this context, please ask me. Anyone, any question? Everything is fine? If everything is fine, I'll go for the indirect functions. That is the solutions based on indirect functions. We will consider the value function. Okay. That is, we will consider the maximum level of utility, or a new utility function v, which is a function of x1 star and x2 star. So u was function of x1 and x2. Now we will consider the derived utility function v, and this derived utility function is a function of x1 star and x2 star. Am I audible perfectly?
Yes, ma'am.
Okay, so now I'm considering the value function, or the indirect objective function, or indirect utility function. Here the objective function is the utility function, so I'm talking about indirect utility function. So indirect utility function will be naturally given by v, which is a function of x1 star and x2 star. x1 star is a function of p1, p2 and m. x2 star is also a function of p1, p2 and m. Our objective is to find out the values of x1 star, x2 star, starting from the indirect value function, or indirect utility function. So we can prove that. Actually, we will like to prove this. x1 star is equal to minus del v by del p1 divided by del v by del m. So since we are talking about comparative static, here the value function, for the value functions, we will take the derivatives with respect to parameters of the model. We will take the derivatives with respect to parameters of the model. Okay, so we will take derivative of b with respect to p1, p2, m, etc. Okay, so these two equations have particular name. These are called Roy's identities. These are very famous equations. These are two very famous equations. These equations are called the Roy's identities. You can write these equations in the form of identities too. So these two are called the Roy's identities. Now to prove this, or to derive the value of x1 star using the indirect objective function, we are starting from the objective function. Okay, we are starting with the objective function. So I hope everybody has pen and paper. So please write down this thing, because the first part, that is this one, this I'll do, and you have to do this part on your own. x2 star is equal to minus del v by del p2 by del v by del m. That you need to find out. Okay, so first let's find out this one, and then you will find out this one. So it will be helpful if you do the steps with me. So we are starting with the indirect function. So v is equal to v as a function of x1 star. As we mentioned, p1, p2, m, and x2 star as a function of p1, p2, m. Del v by del p1, that will be del v by del x1 into del x1 star by del p1. We are using the chain rule. Plus, in x2 also there is p1. In x2 also there is p1. So del v by del x2 into del x2 star by del p1. So this will be the expression. If I take the derivative with respect to p1, it will be del v by del x1 into del x1 star by del p1 plus del v by del x2 into del x2 star by del p1. Now I am replacing del v by del x1. Okay, that is differentiation of utility with respect to x1 by lambda star p1, by lambda star p1. And similarly, del v by del x2, I am substituting using lambda star p2. Now, from where we are getting this lambda p kind of solution. So let's go back to our utility maximization exercise. So if I take the first order condition, we are getting del u by del x or del u by del x1 is equal to lambda p1, del u by del x2 is equal to lambda p2. So whenever we are taking derivative of utility function with respect to x1, we are getting lambda p1, and when we are taking derivative of utility function with respect to x2, we are getting this to be equal to lambda p2. So these two elements we are substituting, lambda p1 and lambda p2. However, here we are using the indirect value function. So instead of x1, we have x1 star, and instead of x2, we have x2 star. So for lambda 2, we are using the star notation. Since it is based on the indirect objective function, actually we have del v by del x1 star is equal to lambda star p1, del v by del x2 star is equal to lambda star p2, this kind of expression. So we are using lambda star p1 and lambda star p2. From this equation, we are taking lambda star common, and we are getting p1 del x1 star by del p1 plus p2 del x2 star by del p1. We are calling this equation number 1. So any doubt, any problem in getting equation number 1? Anyone, any question, anything I need to repeat, anything you need to check? I hope at least few persons are doing these things. If not all, maybe, you are trying to do these things. Anybody, any question?
Ma'am, can you explain the substitution part once more? The lambda star. Yes. How from the first order condition we are getting the lambda star P1.
Okay, so this we did in the last class.
Yes, ma'am, that I understood. But like if we consider the first order condition here, we know that P1 is equal to lambda del u by del x1. So from there, how are we getting lambda P1?
Your objective function just look like this. Instead of x1 and x2, you have x1 star and x2 star. This is the same kind of function. Okay. Initially, we used the notation f, and now we are using v. V is a function of x1 star and x2 star. Nothing else. Am I right?
Okay, ma'am. Yes, ma'am. Okay, understood, understood. Actually, I was considering the first order condition that we did in the minimize problem, so I was getting something else. I understood now.
Okay, so I hope up to equation number 1, it's fine. And then we are considering m is equal to p1 x1 star plus p2 x2 star. P1 x1 star plus P2 x2 star. Actually, this is the budget constraint which we use in context of utility maximization. We replaced all x1 and x2 by x1 star and x2 star. That is, we replace x1, x2 by their value functions, x1 star and x2 star. Differentiating this with respect to P1, the left-hand side is del M by del P1. Now, income or budget is a constant, therefore this is equal to 0. And, P1 x1 star, where x1 star is a function of, again, P1. So, it will be U into V format. So, x1 star plus P1 del x1 star by del P1 plus P2 del x2 star by del P1. x2 star is also a function of P1, P2, M. So, we have to take derivative of x2 star with respect to P1. So, if I take derivative of these budget equation with respect to P1, we are getting this expression. So, from here, we are getting this P1 del x1 star by del P1 plus P2 del x2 star by del P1 is equal to minus x1 star, minus x1 star, okay, minus x1 star. So this is equation number 2. So what I can do, I can replace this part in equation number 1, that is P1 del x1 star by del P1 plus P2 del x2 star by del P1 by this minus x1 star. So what we are getting, del V by del P1 is equal to minus lambda star x1 star. Del V by del P1 is equal to minus lambda star x1 star. Okay. So up to this, we could derive this one, minus lambda star x1 star. We are calling this equation number 3. Finally, we are taking derivative of B with respect to M. First, we took the derivative with respect to P1. Now, we are taking the derivative with respect to M. And applying the chain rule, del V by del x1 into del x1 star by del M plus del V by del x2 star by del M, that we are considering. Okay, so this we are replacing, del V by del x1, that is lambda star P1. So we are using that, and del V by del x2, that is lambda star P2. So again, we are using that expression, and we are getting equation number 4. We are getting equation number 4. Now from the budget constraint, M is equal to P1 x1 star plus P2 x2 star. This we are differentiating with respect to M. So del M by del M, that will be equal to 1. P1, x1 star is a function of M. So P1 del x1 star by del M plus P2, x2 star is a function of M. So del x2 star by del M, that is equal to 1. So we are getting equation number 5. Substituting 5 into 4, okay, this part into 4, we are getting del V by del M is equal to simply lambda star, because this part is equal to 1. So del V by del M is equal to lambda star. This is equation number 6. So now finally, if I consider the ratio del V by del P1, which was minus lambda star x1 star, and divided by del V by del M, which is lambda star, we are getting this expression. Adjusting, cancelling lambda star, we are getting minus del V by del P1 by del V by del M is equal to x1 star. So in this way also we can derive the value of x1 star. This is called the Roy's identity, minus of ratio of derivatives of indirect utility function with respect to P1 and M gives back the demand function, commodity demand function. So next you have to find out minus del V by del P2 by del V by del M, that will be x2 star. So please do that thing, the second part, this one. So please prove this part. Okay, so this way we proceed in this way. So for solving this, please write down the objective function. V is equal to V of x1 star, function of P1, P2M, and x2 star, which is also function of P1, P2M. So instead of considering del V by del P1, now you need to consider del V by del P2. Del V by del P2. With respect to price of the second commodity, you need to proceed. So consider del V by del P2, then go for proper substitution, then consider the budget constraint, take the derivatives, plug in the suitable place, and check what you are getting. If anyone have any question, any confusion, please ask me. Otherwise, please do this thing now. Is it understandable? Will you be able to do it? Are you doing this thing?
Yes, ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Doing this thing? Anurag?
Yes, ma'am.
Doing this thing?
Sorry, ma'am, I cannot hear you.
বলছি করছো, জিনিসটা করছো?
Yes, ma'am, trying.
আগেরটা বুঝতে পেরেছো?
Yes, ma'am, আগেরটা বুঝতে পেরেছি।
অনুষ্কা?
Yes, ma'am, I'm doing it.
Okay. অরিত?
Yes, ma'am.
করতে পারছো? করা যাচ্ছে?
Yes, ma'am.
আচ্ছা। Aryan, what about you?
I'm trying, ma'am.
Got the earlier one? Understood the earlier one?
Yes, ma'am.
একটু ডাউটফুল লাগছে, সবাই বুঝতে পেরেছো কিনা? রাজস্বী, got it?
Yes, ma'am, doing.
হ্যাঁ, কি বলছো?
Yes, ma'am, doing and trying.
শুভায়ন?
হ্যাঁ ম্যাম।
করছো? বুঝতে পারছো? দেখো, বসে থাকলে কিন্তু পারবে না, করতে হবে। বসে থাকলে কিন্তু হবে না। আনন্দরূপা?
ম্যাম
কেটে গেল ম্যাম।
ম্যাম
নাম
করছি।
দিলেন আমার সাথে কেটে গেল।
হ্যাঁ, কি বলছো?
না না, আপনি আমার নাম দিলেন, তারপর
সৌগত,
কেটে গেল বোধহয়।
আমি বলছি বুঝতে পারছো? জিনিসটা বুঝতে পারছো
হ্যাঁ
তো
ম্যাম, মোটামুটি
কি
বুঝতে পারছি।
করছি?
হ্যাঁ। হুম।
হ্যাঁ, প্রচুর এগুলো করতে হবে, টাইম বেশি নেই তো আমাদের।
হয়ে যাবে।
So we have to follow the same style. Need to follow the same style. Find out del V by del P2. Then consider the constraint. Take the derivative with respect to P2. These are very similar. If you understand the first one, you will understand all the varieties. So first we are considering the indirect objective function, taking the derivative with respect to proper parameter. And then we are considering the constraint and taking derivative with respect to that parameter only. Then we need to substitute equation number 2 in equation number 1.
ম্যাম done.
The similar thing we will repeat for del V by del M. We will consider del V by del M. First, we will consider the objective function. Next, we will consider the income constraint. Del V by del M, first for the objective function, next for the budget constraint. And with the help of the two expressions, we are finding or proving the Roy's identity. So this part, second part will be similar because we are considering del V by del M, and then the budget is there and we are taking derivative with respect to M. So this second part is identical. The second part will be identical. Only there will be a change in the first part. Second part will be identical.
ম্যাম done.
Done? Very good.
Yes, ma'am, done.
So just check, whether you got these things. These are the derivatives with respect to P2. So please check everything.
Yes, ma'am.
Got the same result. So just take the parameter for the indirect value function, take derivative of indirect value function with respect to that parameter, then consider the constraint, take derivative with respect to the same, amount, either x1 star, x2 star, etc. So do the same thing, with respect to P1 or P2, do the same thing. Then consider del V by del M, that is objective function you are considering, and that you are taking derivative of that with respect to income, and then you are considering the income constraint and taking derivative of this with respect to M. Getting the values, plug the values in the appropriate place, and you will be able to come to the condition minus del V by del P2 by del V by del M is equal to x2 star. So this is an alternative way to derive the demand curves given the indirect utility function. So given the indirect utility function, we can derive the demand curves in this way. Okay, now when we are doing all these things, we are getting the value of lambda 2. So here, the lambda star is nothing but del V by del M, change in the indirect utility due to change in income. Okay, so this kind of interpretation we mentioned in the last class. It is the, marginal utility of income or marginal utility of money interpretation of the Lagrange multiplier. We add it here, marginal utility of income. Okay, So clearly, when we are taking the derivative with respect to the objective function, clearly we are getting that, the lambda is del v by del m. Okay, so it is marginal utility of money. Del v is the utility, indirect utility. So change in utility, marginal utility with respect to change in income. Okay, so in this way also we will be able to interpret the Lagrange multiplier. Okay, now for the details, etc., interpretation of the Lagrange multiplier, please see Chiang. Okay, from Chiang's book, please look at the interpretation of the Lagrange multiplier in Henderson and Quant. And today I already sent you a book, book by Silverberg and Sven. In these books too, we will get interpretation of the lambda. However, while you will prepare your own note, first you start with Chiang. Expenditure minimization. Okay, the second problem we did the expenditure minimization. So similar kind of exercises can be done using expenditure minimization. So here, instead of Marshallian demand curve, we are considering the Hicks demand curves. So x1 star is a function of p1, p2, u star. Here, the superscript, So there is a typo, star will be the superscript. X2 star will be again a function of P1, P2, U star. And lambda star, that is also a function of P1, P2, U star. So the expressions we have, these are functions of P1, P2, U star. In the earlier case, these were functions of P1, P2, M, and here it will be function of P1, P2, U star, the fixed level of utility. So the value function in terms of expenditure minimization will be given by E, which is a function of x1 star and x2 star. So we are following the similar kind of technique, that is we are taking derivative of this E with respect to parameters of the model. Del E by del P1, we are considering del E by del P1. Okay. Now, what is the equation for the expenditure function? What is the equation for the expenditure function, anyone? E equal to, what is E equal to? What will be the right hand side? Upanita?
Yes, ma'am.
What will be the expenditure equation? E is equal to what? What will be the right hand side? What is your total expense on two?
P1 x1 star plus P2 x2 star.
Yes, P1 x1 star plus P2 x2 star.
The constraint.
And budget constant.
Here it is not constant. We are discussing the expenditure minimization. Here this is the objective function, isn't it?
Okay, ma'am. Okay, ma'am.
Okay, so that I'm asking for.
Ma'am, your voice is breaking.
Ma'am could not hear anything, guys.
Is your expenditure P1 x1 expenditure? Am I audible?
Yes, ma'am. Right now it's fine.
Is it okay now?
Yes, ma'am.
Yes.
However, there is some connection problem. Okay, am I audible now? It's perfect.
Yes, ma'am.
Okay, so I'm asking about the expenditure function, So as you know, E will be equal to P1 x1 plus P2 x2. So please add this equation here. E is a function of x1 star and x2 star, and the functional form of this objective function or the expenditure is given by E is equal to P1 x1 star plus P2 x2 star. P1 x1 star plus P2 x2 star.
Ma'am, are you presenting?
It's not coming?
No, ma'am.
So in the meantime, please write down the expenditure equation. E is equal to P1 x1 star plus P2 x2 star. Is it visible now?
Yes, ma'am.
Yes.
Okay, once you write the expenditure equation, take derivative with respect to P1. So the first expression was P1 x1 star. X1 star is a function of P1. So apply the U into V principle. So it will be x1 star plus P1 del x1 star by del P1 plus P2 del x2 star by del P1, because x2 star is also a function of P1. So is there anyone who is not understanding this first line? So next what we are doing, x1 star we are keeping intact, P1 we are replacing by lambda del U del x1. P1 we are replacing by lambda del U del x1, and P2 we are replacing by lambda del U del x2. So let's go back to the expenditure minimization problem. This was our expenditure minimization problem. So from the first order condition, we got P1 is equal to lambda del U del x1 and P2 is equal to lambda del U del x2. So we are replacing this kind of expressions there. So x1 star has been replaced by lambda del U by del x1. And P2 has been replaced by lambda del U by del x2. Okay. So is there any question regarding equation number 1? Is it understandable? Anyone, any question, any clarification you need? Please try to clarify your doubt during the class, because, we do not have much time. So, some of the students mentioned that they are facing some problems regarding few definitions, etc., and requested for makeup class. I'll be not able to take a number of makeup classes, So please look at the things, and any question you have, any question which is arising in your mind, please ask me during the class, because I'm taking classes on 4 days in a week. So I have very limited time to do makeup classes. Okay, so please remember that thing. Okay, so everyone, I hope is understanding this equation. Then so next what we will first we will consider the objective function, then and take the derivative with respect to the same
And will you repeat?
Ma'am, your voice is breaking.
Ma'am, your
Your
voice
voice
is
is
We
breaking.
can't hear anything.
breaking. Yes.
say here. So here the Hello, am I audible now?
Yes,
Yes,
ma'am.
yes.
Yes, ma'am.
There is some serious thing. So I think you could do this part, or this part is complete. Anyone, any problem with this second part? Because I lost my connection. So please check it. I hope this was fine. And if anyone have any question regarding the second part. Is there any question? Should I need to repeat anything here? Yes or no?
Yes, ma'am, it's clear.
So if that part is clear, we were at this point. Okay, finally, what I'm doing, I'm considering the derivative of this optimum expenditure with respect to U star. Del E by del U star, that we are deriving, del E by del U star. So if I consider del E by del U star, I'm getting P1 del X1 star by del U star plus P2 del X2 star by del U star. Okay, because both X1 star and X2 star are functions of U star. So in the similar fashion, I'm replacing P1 and P2 by lambda del U by del X1 and lambda del U by del X2. So I'm replacing P1 by P2 by these two terms, lambda del U by del X1 and then P2 by lambda del U by del X2, and presenting the equation number 1. Then I'm considering the constraint, that is U star, and taking derivative of this with respect to U star only. So in the left hand side, I'll get 1 del U star by del U star. So I'm getting 1. In the right hand side, I'm using the chain rule. There is a typo. Okay, so here we will not have M, rather we will have U star. So, del U by del X1 into del X1 star by del U star plus del U by del X2, না এখানে ভুল হয়েছে, এটা একটু ঠিক করে লেখো তো ইকুয়েশন নাম্বার 2টা। Equation number 2 will be 1 is equal to del M by del X1 into del X1 star by del U star. Del M by del X1 into del X1 star by del U star plus del M by del X2, M or E, এখানে আমি E notation use করেছি, so del E by del X1 into del X1 star by del U star plus del E by del X2 into del X2 star by del U star. So should I repeat or you could manage it? এইটাতেও ইকুয়েশন নাম্বার 1এও del E by del X1 into del X1 star by del U star হবে plus del E by del X2 into del X2 star by del U star হবে. Actually, I copied and pasted in some places. These are based on heavy equations, so there is some typo. So all these things will be replaced, all U here will be replaced by E. Rest of the things are okay. And here we will have del E by del x1 into del x1 star by del U star plus del E by del x2 into del x2 star by del U star. So once we get this value, plug the value here. So you are getting del E by del U star is simply lambda. Del E by del U star is equal to lambda. Okay, so I'll redo this slide and I'll send you this slide too. And I hope you changed the notations. However, I'll just change the notations and I'll send it to you too. Just a minute. Okay, so here you have to prepare the interpretation of lambda as a shadow price. Okay, so it is your homework. Here the lambda is interpreted as shadow price. It is change in expenditure due to change in maximum level of utility. Change in expenditure due to change in maximum level of utility. So prepare your material, go through the things, go through the references, texts, and please check before coming to the next class, please check all these derivatives, etc., starting from Roy's identity and, you know, all the interpretations of the Lagrange multiplier and, you know, earlier interpretation of the Lagrange multiplier and this interpretation of the Lagrange multiplier. So actually, we have added two interpretations from when we are considering the utility function, be it the original utility function, be it the value function, we are using or we are presenting, you know, the Lagrange multiplier as the marginal utility of money, both in case of utility maximization and expenditure minimization. However, here we are presenting Lagrange multiplier as shadow price. Okay. In Henderson Quant 2, you will get the interpretation of the Lagrange multiplier, the shadow price interpretation of the Lagrange multiplier. So check everything, try to understand the matters. You know, these are quite advanced topics, you know. So Roy's identity, comparative static path, interpretation of the Lagrange multiplier. So check everything properly and then come back. Whatever difficulties you have, we will clarify in the class. And it's always good if you can send me the question earlier, like today. Okay, so readings, Henderson and Quant chapter 2, solve exercises I mentioned in the last class too. However, you are telling that there is some problem in this version of the Henderson and Quant. So I have to somehow, you know, take a snap and I need to send it the exercises to you. Okay, and then do anyone have the book, Henderson Quant book with you, not the soft copy, the actual book? Anyone in the class?
Yes, ma'am.
Okay, so would you please do this thing for me? Would you please take the snap of the exercise and take a scan and send the PDF to your friends, or will you please post it in the Google Classroom?
Okay, ma'am.
Okay. And I sent you another book, Silverberg's book. From Silverberg's book, please check chapter 10, page 252 to 282. There are many things. Next day, we will start talking about output maximization, cost minimization. All these problems are covered in these pages 252 to 282. But this is also another very good text, Silverberg's book. Okay. So I'm closing the thing here. Because of the network today, we faced a lot of problems.